We have another example here of linear motion. Go ahead and read through it. So similar to the previous examples, we need to decide if we need to use calculus relationships or if we can use kinematic equations. As a reminder, I've mentioned it in a previous video, we are going to assume no air resistance or drag. Drag is just another term to mean air resistance. In this particular problem, it's a terrible assumption, but we're still going to assume it. That means we're pretending we live on an Earth that has no air, which of course means the helicopter wouldn't work and we would not be able to breathe. So again, terrible assumption. But again, the reason why we assume this is because we need at least differential equations to be able to solve. And that's not a prerequisite, mathematical prerequisite. So we're starting ideally, simply in that situation. The only thing affecting the package once it leaves the helicopter is gravity. Oh, affected. In problems where we're assuming an object is only affected by gravity, you're going to see the terminology free fall. The physics definition of free fall is something moving only because of gravity. In our everyday lives, in movies, sometimes we use the term free fall for somebody that has skydived, jumped out of an airplane, opened their parachute. That's not the same situation as we're assuming. Gratefully, the air slows them down, they reach a terminal velocity. In our physics assumption, free fall means only gravity. So as an object falls towards the ground, it will continually speed up and speed up and speed up until it eventually reaches the ground. Okay? No such thing as terminal velocity right now, when we assume no air. All right, so approaching this problem, making this assumption that the package, once it has been dropped from the helicopter, we can say that its acceleration is due to gravity, so it points downwards, so negative, and g, the acceleration of gravity, 9.8 meters per second squared. Total side note, the test notes, you don't have to remember, oops, I'll just highlight it there. You don't need to remember the value, it's in here. It's also on the front cover of the test notes. And this reminder that the acceleration of gravity is downwards, is negative g, if we're calling upwards positive, which we're going to go ahead and do that. So similar to the previous example, because this acceleration is constant, we will be able to use the kinematic equations. In place of s, I'm going to go ahead and use y, because we're talking about vertical motion in a coordinate system. When we're measuring up or down vertically, we call that the y-axis. So that's why I'm going to call this y. So similar to the last problem, let's make a table of the variables that show up in these equations. And we're going to draw a rough sketch, choose an origin such that we can fill this in. So let's say we have our helicopter. It's somewhere up here. Somebody is holding this package out the door, out the side, and they're going to let go. They're going to let go of the package. Now, because the package is in somebody's hand originally, it is moving upwards with the helicopter at 15 meters per second. The package is still going to have that velocity even when the person lets go, because the package was moving with the helicopter. So this diagram, this rough sketch I'm drawing, I'm representing that this package is moving upwards at 15 meters per second. That moment the person lets go. That means the package is going to go up farther and then turn around and head back down. With this rough sketch, we want to go ahead and draw a coordinate system to use. Because the helicopter was moving upwards, all the motion is going to be along the y-axis. So we just want to choose a y-axis to be somewhere, which of course makes sense to go ahead and make our y-axis the line that the package will move along. Our x-axis, so that we're defining the origin, it doesn't really matter if we choose to put it where the package is, initially or at the ground, either way works. Let's go ahead and put it where the package is initially. Again, the only reason I'm drawing the x-axis is so that I'm defining the origin. I'm defining the origin to be where the package is initially. That means I'm saying y initial is 0. It tells us that it is moving upwards at 15 meters per second. Again, I'm just writing the positive sign to remind myself that I'm accounting for the direction upwards. It tells us the package takes 18 seconds, so that's time, before it hits the ground. So the package finally is going to be down here at ground level, which means y final is going to be negative. Ultimately, it's asking how high above the ground the package was when it was released. So we're essentially looking for y final because that represents how far below the origin the package will be. We know acceleration is downwards at 9.8 meters per second squared, so I can fill that in. V final. V final is the tricky one here. We really want to say V final is 0 because it's totally going to hit the ground, get smashed, and come to rest. But we cannot put in V final of 0. This is very important to understand. These kinematic equations, these big three, can only be used if acceleration is constant. While the package is moving through the, well, we're pretending we don't have air, but through the air, it is constant. But as soon as the package comes into contact with the ground, it actually has a new acceleration, a different one. That acceleration is from the ground pushing upwards, causing it to slow down and stop. So V final in problems that involve just gravity, just free fall, we call this the impact velocity, meaning the velocity, the moment, that split second before the object hits the ground. In this case, we don't know what that is. So this is an unknown. Our other unknown is y final, which is what we want to calculate. So let's look at our kinematic equations and see if any of these equations will allow us to calculate for y final without finding v final first. Though we could find v final first, theoretically. So our top equation, we do not know v final. We do know v initial. We do know acceleration. We do know time. There's one unknown. We could totally find v final here. Technically, we don't need to. Because if we look at the middle equation, we don't know y final. That's what we want to find. Y initial we know, based off of the coordinate system we chose. We know v initial, we know time, acceleration, and time. So there's only one unknown here as well. So we're going to use that. I do want to point out, though, in the third equation, we don't know v final, we do know v initial, we do know acceleration, but not y final. There's two unknowns here. It would be totally valid to find v final using the top equation and then putting it into the bottom equation to find y final. Perfectly wonderful, valid way to solve the problem. But again, because I can find y final from just the middle equation, I'm going to use that one because that's what I'm asked for. But there are a couple ways to go about solving this problem. So as usual, we want to write out the equations that we are going to use symbolically so we can represent what we're doing. I do plug in zeros. So because we have defined y initial to be 0, I'm going to go ahead and cross that out. We're solving for y final. We can go ahead and plug that in. So v initial is 15, time is 18. 15, it is positive. I wrote that in the table. You can write that in the equation when you go to plug it in if you want. 1/2. Our acceleration is downwards at 9.8. It's important to have the negative sign on there. And then the time is squared. So we simply need to plug and chug at this point. Just go ahead and put our numbers in and solve. Plugging this into my calculator tells me my final answer is negative 13.17.6. Which of course I cannot leave it that way because I do not know the answer this significantly. I do want to point out, what do we mean by the negative sign? Every problem that we do, plus and minus, the sign is always dependent and determining the direction in the coordinate system we're talking about. So coming back to our rough sketch, having a negative answer totally makes sense because the package ends up below where we put the origin. We put the origin where the package was released. Having a negative answer means it ends up below where it was released. Now the problem's asking us only how high above the ground. I'm going to call that H. We're not going to put the negative sign because that deals with the direction. When it asks for how high, it's just saying how far. Now, the other thing to keep in mind is we can't leave our answer with that many digits. So coming back to the problem, the 18 has 2 sig figs. The 15 has 2 sig figs. G has 2 sig figs. So our answer needs to only have 2 sig figs. Rounding, after the 3 we have 1, so you could also say 1.3 kilometers if you want, that's fine. Or 1.3 times 10 to the third. Any of those would be accepted. The only time you're going to be strictly enforced to a certain unit is if the problem specifically asks for the units to be, say, kilometers versus meters. So, I need to put my meters there. So, any of those would be accepted. If you notice the approach in these last 2 sample problems, so sample problem 3 and 4, both of them have used the kinematic equations. So we've approached them similarly. We've set up this table to fill in the variables that show up in the kinematic equations. We've drawn a rough sketch with a coordinate system. That coordinate system is essential. You can put it wherever you want. You just need to base your initial and final position and all the plus and minus signs based off of that coordinate system. Please reach out to me if you have questions. I'm always happy to help.